Welcome back, everyone. We're going to go ahead and start oral session number 2. This one is titled Data-Driven and Physically Based Modeling. And we will have 6 presenters. And just to remind you of the format, there will be 5 minutes of speaking and then approximately 5 minutes for question and answer. And a reminder that each of these presenters have a pre-recorded long-form video available online through the QR link. So our first speaker will be Reza. Go ahead and come up. Let's welcome Reza.
Can you hear me now? Okay. So hi everyone, my name is Reza. I'm a PhD student in hydrology, and today I'm going to briefly recap my presentation about nowcasting nets. So first I will go through what motivated us to do this study, and basically precipitation drives many of the natural hazards, including flash floods, landslides, and it is really important to have actionable predictions of precipitation. On the other hand, this is a pretty challenging task because of the complexities of the atmospheric dynamics and also lack of sufficient knowledge about how precipitation systems evolve in general. There are different sources available for precipitation, including gauges, radars, and probably satellite remote sensing is one of the most popular one. But the problem with the satellite precipitation products, and specifically merged precipitation product, is that there is a gap between when precipitation, when satellite observations are made and when the precipitation estimates become available. So this is the problem that we wanted to tackle in this study. There are conventional nowcasting methods which are used in the community, but the problem is that most of them cannot handle big data, and they have other limitations as well. So we were looking for an alternative for precipitation nowcasting. And since deep learning has improved a lot in the past few years due to the increase in the computational power, we decided to develop nowcasting models using deep learning to mitigate the latency gap of satellite precipitation product. So basically, we developed 5 nowcasting nets, which are listed here, and compared them with 4 other benchmarks, which are namely random forest, linear regression, a persistent benchmark, and also optical flow, which is probably the most popular method for precipitation nowcasting. Our study was focused on the CONUS, and we used iMerge early, which has 4 hours lag from real time, and we were planning to mitigate this gap, this lag. We used precipitation maps from the Eastern CONUS to train and validate and test our models, and then we tested the models further over Western CONUS, which precipitation maps were not used during the training. I will quickly review 2 of the experiments that we did in this study. There were totally 13 of them, so if you are interested, please check the paper. But here we see overall performance of the models for 90 minutes lead time. In the Eastern CONUS, there are 8 metrics provided here. In general, CNC and RNC models provide the most stable results. And by stable, I mean the performance doesn't degrade over time as the lead time increases. CNC model, convolutional nowcasting nets, provide also the best performance. For example, in terms of the MSE, it achieves 42, 24, 18, and 16% improvement compared to benchmark, linear regression, random forest, and optical flow model. Here we also see a case study for a lead time of 90 minutes, which is a frontal system. And if you look at the top row, which I'm pointing at, you see that the system is changing, the shape of the system and intensity of the system is changing dramatically. And then in the next rows, you can see the lead time, and different columns shows different models developing this study. And the last column on the right shows the observations. Again, we can see that the CNC model has the best performance. It's able to capture the intensity changes in the shape of the precipitation system very well, which is reflected through lowest MSE score and also highest correlation coefficient with the observations. So basically, the finding of the studies is that the CNC architectures that we developed has a lot of capabilities, and it can learn the spatiotemporal dynamics of the weather systems evolution, We also use the novel technique of the novel Monte Carlo dropout technique to provide uncertainty associated with our estimates. However, there are challenges associated with deep learning models. Computational power is one of them, and probably the most important challenge for the deep learning nowcasting, precipitation nowcasting using deep learning is that precipitation nowcasting itself is very challenging. It is even more challenging than the video frame prediction, which is a common practice of deep learning in the computer science community. So at the end, I would like to thank my co-authors here, Dr. Hoshin Gupta, my advisor, Dr. Ali Behrangi from our department, and I'm ready to answer the questions.
Thank you, Reza. We'll take questions in the room, and people attending virtually can answer their questions in the chat.
Hi, Reza. Very interesting. I actually also paid really good attention to your longer video. So I might ask you, so I have a couple of questions, which might be from the presentation, the long video. The first one is so to predict, you have to train the model. So I was wondering, do you have to retrain it for as time goes, or you just retrain it once and then it works for all future times? Because the climate system changes. So I was wondering if it still captures it if you train it once. The other one that I have is that from your results, I saw that your method is 60% better than optical flow. So I was wondering, is 60% better enough to justify using your method? Because because the other issue is complexity, right? You know, which one is more complex or whatever. So I'm wondering if those 16%. And also, third and final, is the code available? Thank you.
So regarding your first question about if the model need to be trained every time, that is no, that is a no. So the model is trained only once and it can be used. So here I have some supplementary slides. Okay, so this is for another case study here. Again, you can see that our model, despite being used on the Western CONUS, which was never used during the training of the models, it still is able to capture the spatiotemporal development of the systems. So it shows that it has learned something. It doesn't need to be retrained again. But if you retrain it again, obviously the result would be better. The second question was about the 60% improvement compared to the optical flow method, which I think is very significant and shows that it has very real world applications. What was the third question? Sorry, I forget that. Okay, yeah. So there is no complexity associated with using the models. There are complexity associated with training the models or implementing the code. Yes, I agree with that, but the implementation is super easy and the code is available on my GitHub page, so you can check that. I just remembered this.
Thanks, Reza. Well, I'll be looking. Reza made the website, by the way.
Hey, nice talk. This is really cool work. I was just wondering two things. If you ever looked at a different test train split, because Western and Eastern have, you know, significantly different topography and all of that. And then my other question was, have you looked at just ensembling all of your models and see if that outperforms any single model?
So I think I mentioned that we use the Eastern side just to train, validate, and test. And the Western side, precipitation maps from the Western side were completely independent. So we never use them during the training, and the performance is completely showing how much they have learned. The second question was about, I have a very bad memory, I guess.
We're going to have to pause and move on to our next presentation.
Okay.
Can you
So you can reach me. Thank you.
follow up after the session? Thank you, Reza.
We'll pause.
Our next presenter is Luis.
Hello, can you hear me? No? Better now? Better? Okay. Keep it there? Better? Okay. Okay, hello everybody. I'm going to present HydroLCM, a hydrological approach to LCM machine learning based modeling. My name is Luis de la Fuente, and I have been working with PESA, with Hochin Gupta and Laura Condon. So probably everybody can have the idea that machine learning is kind of black box with some input and output, and really we don't know what's happening inside. So for this reason, we have the question that we could extract knowledge from that using from the parameter and the state variables to learn something. And specifically, if LCM is a good structure to extract knowledge, or maybe we can improve it. So first, what is LCM? LCM is a recurrent neural network with gate operator to control the flow of information in each neuron of cells. This is the traditional figure that you can find in different papers and internet. And really, it's very hard to understand what's happening there. But my key message here is that really what we are doing, or the equations that are inside, are the same that we are using when we are solving a water balance. In fact, the S that is here is the same like C over there. The runoff is the same like H, and input are the same like the X is the same like precipitation and evapotranspiration for different time steps. But there are some issues with this structure. And one of these is that LCM is doing a reinitialization of the state at each time step. And the recurrency, in some way, the use of past information is used to guess what is the state now. That this is not a way how we are used to deal with the context. So our proposal, we are proposing HydroLCM, a new structure, where the change that we are doing, we are tracking the state all the time, so we are not losing information. We are updating only one time using the input gate and output operators. And now the context is given directly as input. So what does that mean is that, for example, we have 10 days of precipitation, the model has the chance to choose which one of these precipitation is more important. The same like evapotranspiration here. The experiment design. Our goal is the comparison from LCM to HydroLCM and the different situation. The framework, we are using 20 models with different hyperparameters, where we have different number of cells in parallel and the different number of memory in the past. And we are training this with 10 different catchments. Here we have in yellow dot, the catchment that we are using, and behind red, blue, and green are catchment, or the catchment that are coming for this paper, where they did a study to analyze what is the flooding mechanism across all the country. So in that way, we can see kind of regions, and our hope is that this new structure should learn this kind of pattern. Some results, when we did the comparison in representation, here is the number of cells that different structure is using. So in almost all the cases, HydroLCM is using less number of cells, 1 or 2, and we had only one case where it's using more. So that means in some way that the representation in the state is a parsimonious representation of the state versus what LCM is doing. And now if we analyze the parameters, what this machine learning is learning, for example, here we have these two catchments, and it's kind of clear that the region should be kind of recent rainfall dominated. And what we learned from the parameters directly, when we open the box and we analyze the parameter or the weight that the machine learning this new structure is learning, we can see that the weight for the precipitation from today is the most important. And then we have this kind of exponential decay in importance. Another example here is clear that, at least for me, that this catchment here is in a region where we have historical rainfall dominated. And what HydroLCM is learning is that the precipitation for the 3rd and 4th days are the most important, but really almost all the precipitation in the past is important. So that's much exactly what we had from the previous study. So in conclusion, HydroLCM is learning a parsimonious and interpretable representation for each catchment. And this way, little by little, we are opening the black box. Thank you.
Thank you, Luis. We'll take questions now.
Great presentation. I just have a quick question. For the catchments that you're analyzing, what made you choose those specific catchments?
The idea from the catchment, maybe here. In some way, we took two catchment from all the different regions we have here. So we have that region dominant catchment. We have another region here in snowmelt dominant. So we picked two from different regions.
Hi, very interesting discussion. I have a couple of questions. The first one, because especially from the longer video, I saw that you're actually modifying the recurrent neural network. So I was wondering, what are you using? Are you using PyTorch or Keras? PyTorch, okay. And then the other question is, I guess, so the project is mostly about trying to render the machine learning transparent than actually like seeing how it performs versus other ways of predicting, right? That's the goal right now.
Yeah,
okay.
This is the idea, try to understand what is behind. But anyway, what I didn't present that, but in the videos is there, that the performance that we are getting with the true structure are almost exactly the same. So we have an interpretable model, but with almost the same performance. So we are not losing that. Ty?
No.
It is hard to hear without a microphone.
No problem. Really nice, Luis. So it seems like the storage that you're modeling is kind of a basin scale storage parameter, and you lose all of this internal connection, this local connection. Can you comment on why does it work if it's still so upscaled? If I understand.
Yeah, good question. From my point of view, what we are learning here is that it's kind of let me see there. This kind of pattern that we are learning here to this is related exactly with some property of the catchment. So this is exactly probably what we will be able to transfer for other catchment that is similar. The question is how we can decide what is similar. And this is what is machine learning when you add some attributes. So the idea is exactly when you add attribute, the machine learning is able to transfer this shape, this feature to another catchment. So in some ways, it's the way how we are transferring information.
Thank you. Let's thank Luis. Next presenter is Jatal. I'll welcome you up to the stage. Transition.
Can you hear me well? Thank you. So, sorry. Hello, everyone. Thank you for being here. This is Jaital Agnihotri. I'm a second-year PhD student at the University of Arizona. I'm working with Professor Ali Bairangi and Professor Gyo Yunu. Here, I'm working on investigating the impact of frozen soil representation on high-resolution stream flow simulation at the continental scale. So frozen soil would affect the magnitude and timing of stream flow. Lab-scale experiments show the presence of ice in the soil matrix. It largely reduces permeability, while other studies at field scale suggest that effect of frozen ground on snowmelt infiltration are based on the vegetation cover and the spatial extent. So due to the lack of understanding of the conflicting phenomena at different spatial scales, land surface models, they tend to parameterize the hydraulic properties of frozen soil in opposite directions. So some focus on increasing or some focus on decreasing the infiltration capacity of frozen soil. We aim to address this knowledge gap and improve the understanding of the effects of frozen soil on timing and magnitude of stream flow at catchment scale. This is the schematic layout of the methods where we achieve the objectives through using the NOAA-MP land surface model with optional frozen soil parameterization schemes, including schemes of supercooled soil water options, 2 options, and soil hydraulic property, 4 options. Additionally, NOAA-MP model is forced with GPM iMerge final precipitation product and NL-2 precipitation product to address the uncertainty in climatic forcing. These models are driven by NL-2 atmospheric forcing. Combination of these form 16 model scenarios. NOAA-MP is run with these 16 model scenarios to produce runoff simulations over continental United States. And we further use the rapid river routing model to route the NOAA-MP model, models like surface and subsurface runoff at grid cells to produce daily stream flow at 52 USGS gauges in the Mississippi River Basin from 2015 to 2019. These outputs are used for further statistical analysis. Frozen soil parameterizations considered in this study are presented here. 2 supercooled soil water schemes are implemented. First is the use of a general form of freezing point depression equation. And second is iteratively solving the variant of freezing point depression equation. For soil hydraulic properties, first method is used in NOAA-MP, which considers fractional permeable area in the grid cell, accounting for more permeability in the frozen soil. The other 3 methods consider frozen soil has more effect on infiltration, and hence it is less permeable, solving different equations for soil hydraulic conductivity and water retention curve. The table on the right, this table shows combinations of frozen soil schemes and how corresponding model scenarios are formed. So moving on to the modeling results, KGE performance metric was used to evaluate the model results, where KGE of 1 would mean optimal performance. The figure shows performance improvement in KGE when scenario 5 is implemented as compared to other scenarios. And interestingly, performance improvement in the range of 20 to 57% was obtained when model scenario with a higher infiltration scheme is used as compared to other models with lower permeability schemes. However, S1 and S5 perform nearly similar. So no obvious improvement are obtained when different supercooled saltwater schemes are used. Based on this analysis, S5 performed better than other scenarios and was chosen as the best case scenario. This plot shows spatial distribution of KGE performance metric and its improvement. And the red dots show the improvement with improvement, while the blue dots show improvement with scenarios that are performing better, other scenarios performing better, as seen in the plot on the top right. Here, the supercooled saltwater schemes have negligible impact in improvement, and the bottom left plot show that more improvement with scenario of higher hydraulic conductivity is obtained. And the plot on the bottom right, it shows the iMerge precipitation improves performance more than NLS forced precipitation. So in summary, tying all the results together, the supercooled saltwater scheme has negligible impact on modeling the stream flow. In contrast, higher infiltration in frozen soil improves prediction of river discharge simulations when coupled with river routing model. And lastly, iMerge driven models perform better than NLDAS driven models at majority of the gauges. As iMerge is a global precipitation product, these results can be tested in different watersheds to check for their efficacy. Thank you for your attention, and let me know if you have any questions.
Thank you. We have time for 1 or 2 questions in the back.
So I actually have two questions. The first question is about how the frozen soil, the hydraulic process is represented, right? So when you have ice in the pore space, it will block the flow pathways, but the freezing and thawing process can also generate cracks. So I'm wondering how that is represented in the model. The other question is how you parameterize the model. So in different places, we can imagine that the depth of the frozen soil might vary. And is that depth information available?
So for your first question, the model does incorporate like the micropores and micropores, so fractional permeable area and impermeable area in a tile. So it does account for that in the soil hydraulic properties, so soil hydraulic conductivity, and as well as the water retention curve. And the second question is about the depths of the soil. So NOAMP has 4 soil layers, and it does go deeper until like I believe so 40 centimeters as deepest soil layer for the deepest soil layer.
We have time for another question. Okay, thank you.
Okay, no worries.
So our next speaker is Camilo. All right, let's welcome Camilo.
No. Hello. Yeah. Okay. Good afternoon, everybody. My name is Camilo Salcedo. I'm a PhD student of civil engineering with the advisorship of Dr. Dominic Bocelli. And today I'm going to present an approach for the near optimal selection of a set of multi-confirmatory sampling locations in water distribution systems in order to characterize a contamination event. The contamination events in water supply systems are a public concern despite they are intentional or unintentional. They can be detected through different algorithms. In this case, they look for anomalies in the water quality parameters. That's why the sensors plays a very important role in here, but the problem is that the fixed sensors can be expensive and can be very specific for a certain contaminant. That's why this research seeks to a way for how to fully characterize the status of a contaminant event in the network in a cheapest way or a more handy way. In this case, we're going to use the confirmatory sampling locations, which can provide us with new information just by grabbing some samplings, for example, in the network. In this case, our problem will be stated based on a water distribution system. We're going to have an injection point, which is going to be unknown. We're going to have a set of fixed sensors, a probability of contamination at each junction, the connectivity between all of the junctions in the network, and we're going to locate a set of sampling locations. The question is, which is the set of sampling locations that are going to provide the most information about the system to us? In order to answer this question, we're going to set a problem. In this case, our primary information is mostly the network, the contamination, a metric. In this case, we select the network entropy and a set of fixed sensors, and we are going to use an optimization method, which is going to seek to minimize the expected network entropy. In this case, the entropy is a measurement of the uncertainty in the network about the event. This problem is going to be subject to 3 different constraints. The first one, the capacity of the authority to deploy the sampling systems in the network. The second one, hydraulic constraints such as energy and mass conservation. And third one, that the fact that a sensor cannot be a sampling location. Therefore, we're facing here a huge problem that is called an NP-hard problem. So we're going to use an approximated method called the genetic algorithms, widely used in water supply systems, to solve and to achieve a near optimal solution for this problem. So real quick, our problem starts with the initial generation. Each individual is basically a network with a different set of sampling locations located in it. So we can create as many individuals as we want in any generation. Then we're going to evaluate them using this fitness evaluation. Basically, we want to rank them from the worst to the best one. And for this, we are using Visual Studio, a script based on C programming that is coupled with EPANet, which is a hydraulic solver. After that, we have to check for the convergence of the algorithm. In this case, if we have achieved a situation in which we are not fully convinced of the results, we can perform the reproduction. In this case, we're going to select just two random parents using the binary tournament and use these operators such as crossover, mutation, and elitism in order to create a new generation. This generation is going to be tested again using the fitness evaluation, and we are going to loop around until we achieved a good result. And finally, we're going to determine which are the set of these sampling locations. For testing this network, we have tested up to 5 simultaneous sampling locations using this little network called network tree. Some quick results. First, we can see here that in the y-axis, we are showing the reduction in the uncertainty after adding a location in the system. And here we can see a clear trade-off between the quality of the solution and the computational time, because we want to make this in real time. Also, we can see here the diminishing returns of adding a sampling location as an aid for the decision maker in order to select the most appropriate number of sampling locations. Finally, some conclusions. These genetic algorithms correspond to the first approach to extend this confirmatory sampling location from single approach to multiple approach. Here, the results are consistent with the results by sampling just one at a time. And finally, we're going to test more approximated methods in order to make this in a real-time basis. Thank you very much for your attention.
Thank you, Camilo. Well, we have time for questions. All the way in the back.
So it looked like from your figure that you had one known location of the release, or is this an optimal set of observations no matter where the release is made?
Okay, that's a really good question. In this case, we have been testing just a single release over here. But the idea in this algorithm is that we don't know where is it. That's why in the previous part, in the foundational research of this, we are using an algorithm called PCSI, which is in charge of locating of telling us which is the most probably source of the injection. But the idea is that it works for any location that is in the system.
Is there another question before we move on?
I have a question.
Okay.
In uncertainty analysis, there's the things you don't know, and the things that you don't know. Can you talk a little bit about different types of uncertainty in your analysis with respect to what you don't know, and what you don't know.
Okay.
I should be a politician.
Yeah. In my case, I'm just working with two types of uncertainty. The first one is not presented here in the presentation. It is regarding the demands. So for example, as we are working on this in real time, we are forecasting to the future. So we can have like a huge spread of the demand, because if we have a contamination event, it is likely that people stop consuming water or start consuming more in certain places. So that's the first type of uncertainty, how the demand will behave. And if the demand changes, we're going to have that these patterns over here are going to change as well. So that's the first one. This is not presented in this presentation, but that's something that we are working on. And the second one is the uncertainty on which locations are contaminated or not, because here, these red dots represent that we have a probability that that junction is contaminated or not. So in the future, with the forecast, we're having here uncertainty. That's why we use the entropy theory to try to reduce the uncertainty by sampling in different sites. That's like the wrap up of the question. Okay.
Thank you.
Okay.
All right, let's thank Camilo. We have two more speakers, and I just want to note that we're exchanging their order because our final speaker will be online. So our next presenter is Yuan. Let's welcome Yuan to the stage.
Can you guys hear me? Okay, so today. Okay, so today I'm going to talk about how to bridge the physical-based modeling with machine learning. So we have two major goals for my current research. The first is to improve the AI interpretability of the AI model, and the second is to improve the physical-based model using machine learning technology. So when we model the Earth system, here is the rainfall runoff process figures. We typically have two methods. The first one is we use the physical understanding to make assumptions. So the most popular method people they use is including a dimensional process at a point scale, or you can try to include more detail at the final resolution. And the other method you can use is you can use machine learning model by using observation data. So for example, you can use NN network to construct very complicated relationship, or you can use a tree-based model algorithm to uncover the decision criteria. So it just depends on what test you want to do. And in my previous study, to compare these two modeling systems, I compare these two modeling systems applied to the snowpack modeling problem. And here, the Snow 17 is the physical-based model. It takes precipitation and temperature as input and use elevation to generate the pressure at the air pressures. And the long short-term memory network contains 3 gating operations, and it's really good at predicting the input state output dependency. But it's a more data hungry network, so you need more data to learn the structure. And when I apply these two methods to my snowpack modeling problem at a continental scale, at 5 different locations, we use the spatial sampling to reduce the computational cost. And if you look at the performance metric at the right, you can see, if we focus on the median of the performance, you can see that actually the machine learning is far better than the Snow 17 physically based model in terms of predictive accuracy. And by the way, we are testing on the 5,000 different locations. So the machine learning also has a better spatial transferability. Another question we can look at is if we trying to predict at 5,000 different locations, actually one single LTM is enough. And you only need us to have 0.26 million parameters, but we have to train Snow 17 at each location. And each location, you got 10 parameters for each location. And if you want to apply to 0.31 million snowy pixel, then you actually will require 3.1 parameters. So this is also saying that the machine learning is also more computation efficient than the physical-based model. Okay, so I think the next question I believe to ask is how can we combine these two modeling, the advantage of these two modeling systems in terms of, because we have a better physical interpretability in physical modeling system, and we have a more accurate predictive power in the machine learning model. So our proposal is actually to look at the isomorphism between these two modeling systems. Okay, so this is the standard LSTM network. You can see the equation is very complicated. It depends on the input X at current time state and the hidden state at the previous time state H. So here, if you look at the top panel, you can see this is the simplest hydrological model I can think of, even without considering any potential evapotranspiration for the rainfall runoff. And if you look at the isomorphism, what I mean by isomorphism is you write out all the equation and try to take away some over problematization part for the LCM. You actually can get really reduce parameter number of version of mass conserving LCM. And in this case, your input bypass scale will equal to 1 to ensure a mass balance. You assume all the water precipitation coming to the system. And the forget remember gate is now control the update of the internal states. And the output gate right now is control how much water will release to the outlet of the catchment. And the point I want to make here is actually no matter it's a physical-based model or the deep learning model, it can be represented as many different links and graphs. And yeah, so for today's presentation, I'm using a specific architecture called infinite gating nonlinear reservoir. And basically, the reason we call it infinite capacity is because we right now assume all the water coming to the system. And the function, gated function, can be any reasonable form so that we can learn a better context. And for today, the loss gates only depend on the PET. Here we also introduce another gate called loss gate, because if we don't consider loss, then there will be no reasonable result that we can obtain. So when we apply to Leaf River, 5 years for training, another 5 years for testing, we actually get a pretty good performance, KG equal to 0.78, but we still observe several model inadequacy at a low flow regime. And here I show the conductivity function. Actually, you can see that the conductivity function, the output gate is trying to learn a sigmoid shape like function, and the PET is a more linear relationship with loss gate. And we can actually also plot a 3D plot for the remember gates. And this also made a lot of sense because the catchment tend to release small water when the storage and PET are small. Okay, so our future work will definitely switch from single cell to a multiple cell structure. So there are multiple ways we can approach to this problem. We can look at the isomorphism for more multiple nodes and write out the equation, or we can just purely use the functional approximation, which basically is taking our ICGIO node and then just mimic the high-mass hydrological model structure, and yeah, to see whether by adding complexity we can improve the performance. So I think I will stop here and taking questions. Thank you.
Thank you. We have time to take a couple questions. We have questions in the room or in the virtual Zoom.
Luis, you must have a question. I have a question. Do you think that this work is going to open the so-called black box of machine learning? And if so, what are some of the missing components? What are some of the things you need to do to open that black box a little bit more?
So I think to open this box a little bit more is you have to be aware of the trade-off between the physical interpretability and the predictive accuracy, because the machine learning is good is because it has more parameters. But if you got more parameters, it's not really, it's not that easy for you to have a meaning for each parameters. So you have to, what we are doing right now is sort of like we are trying to on top of the LTM theory to explain the physical based model. So for example, when we do the isomorphism, actually right now the gating function is equal to the process parameterization in the land model or in a hydrological model. So that when we, on top of this theory, we can make it more explainable. And also when we put in the gate function right now, I'm just using a single sigmoid function. And if we can put a more complex function, actually we can, achieve a more better predictive performance, and we can, based on the current physical structure, and then you get a more complex function so that people will still think, oh, this is a physical-based model. But you got more flexibility for learning the correct physics. Yeah.
Thank you. There's one question back there.
So as I understand this, you've married a empirical hydrologic model with your machine learning model. What water catchments are you going to test it on?
Oh yeah, so I forgot to mention that I was testing on Leaf River. So it's around Mississippi. It's a pretty wet catchment. So that's also the reason why when we get the remember gate, when we plot the gate function states, the remember gate, actually each gate is between 0 and 1. And that's why the reason the remember gate is always above 0.9, because the catchment tend to store more water inside the catchments. Yes.
Thank you. Let's thank Yuan. Our next presenter is Sidian, who will be joining us via Zoom.
Okay, hello. Hello, everyone. I'm Stian. So I'm a PhD student working with Dr. Bogo. And my topic for today is to model flow, transport, and phase change in shale rock in the deep subsurface, which will apply to shale gas production. So in shale gas production processes, one interesting observation is that if you look at the fluids that are coming from this shale formation, the ratio of the gas compared with the liquid is much greater. And over time, this so-called gas liquid ratio will increase, which you can see on the right figure. And the challenge is that if we use the model that has been well established in another kind of reservoir, which is the conventional reservoir that has been producing oil and gas for a long time, turns out that this model failed to predict this high gas ratio or liquid ratio from shale. So now the question is, why do we have this high gas to liquid ratio? And one leading hypothesis is that within shale rock, the thermodynamic phase change behavior of the fluid will become abnormal. And in specific, because in the shale rock, the pore spaces are very tiny, on the order of nanometers. And there are some additional physics, which is the so-called nano-confinement effect that will lead to a deviation of phase behavior compared with the bulk, which is in the conventional reservoir. And we show an example using the figure on the right, where the orange line is the phase behavior in a nanopore, while the dashed line is for the bulk. And this deviation will depend on different pores. In addition to that, if we look at the shale rock, it will contain complex pore spaces within which we may have this flow of liquid and gas. And this interaction of phase behavior and flow and transport in these complex pore spaces may eventually lead to this high liquid to gas ratio, high gas to liquid ratio in shale reservoir. However, this has not been well understood yet. So to test this hypothesis, we developed a mathematical model which allows us to simulate this coupled phase change, flow, and transport processes in shale rock. And here we show the formulations for the model, which I will not be able to go into detail here. But the key idea is that given a shale rock, we can represent the pore structures within the rock with these network pores, which we call it the pore network. And for each pore of the network, we can formulate the governing equations for flow, transport, and phase change in the pore. And finally, by solving the equations for the entire network, we can look at how this phase change, flow, and transport within this shale rock. So here we saw some preliminary results where we have this pore network that are initially saturated with liquid, and we inject gas from the boundary. And for comparison, we simulate one case that without phase change, which is on the left, and the other one with phase change on the right. And note that here the phase change, we didn't include a nano-confinement effect yet. But still, as you can see, when phase change is happening, it will generate a preferential gas pathway, which indicates that you may have more gas coming through this pore network, and which we speculate may be one of the reasons that we have this high gas to liquid ratio that we observe in the reservoir. So finally, to summarize, we have developed this model that represents two-phase flow dynamics, transport, and also phase change within these complex nanoscale pore structures in shale rock. And we present some preliminary results to show how these phase change and flow transport processes will look like for a given pore network. And as I mentioned, we haven't included the nano-confinement effect yet. So in the future, we would like to incorporate this nano-confinement effect into the current model and perform more comprehensive analysis and simulations to look at how would the thermodynamic phase behavior and flow behavior looks like for shale rocks. And eventually, the ultimate goal is to couple this new model or apply these new understandings from this model into the reservoir scale simulators so that we can improve the prediction from the reservoirs and also come up with better strategies to explore this gas and from the shale reservoirs. So with that, I would like to thank you and take questions.
Thank you, Sidian. Do we have any questions in the room? One in the back, two in the back?
Hi, Sidian. I was just wondering how you could incorporate the findings of a nanoscale model like this at the larger reservoir scale if you don't necessarily have that data resolution to do so. I was just wondering about the process in doing that.
Yeah, so that's a great question. And as you may know, so we are looking at this very small pore spaces. And if you want to apply in the field, that you will have a very large shale rock, and you don't know it, and you can the computational cost will be very large. If you want to apply it, then that's not feasible. So one possible method is that we can, from a small rock sample, we can derive some constitutive relationship from this model, like say the phase behavior and also the relative permeability curve for the fluid flow and also the PCS curve, something like that. And then we can develop this IEV scale relationship so that we can apply into the reservoirs so that we may be able to improve the reservoir scale simulations. Yeah, but this is a difficult problem, I would say, yeah.
Thank you. We have one question in the back and then we'll move to, we have an online question as well.
Hi, Sidian, great work again after last year's as well. So looking at the transient simulations, I mean, they're really fascinating, but I'm wondering if you could go straight to a steady state solution and maybe then relate to a static parameter like interfacial area or something like that, or surface area. So I'm wondering if there's any value in a steady state solution.
So, yeah, that's a great question. So previously we have shown a model that we assume static, which and to derive upscale parameters for at the IEV scale. However, this cannot be represented. So this static assumption may or may not be applied because we have these dynamic processes. And but I think it's possible that if we can use these steady state simulations to derive some upscale variables I have mentioned in the before, and then compare with these dynamic simulations and to see how the difference between these steady state and these dynamic processes, we might be able to identify some cases where the steady state will work very well, and also identify some cases which may not be very well. Then after that, we can use those working very well to the field, and also think about how to improve that improve those cases where the steady state doesn't work very well, and then we can come up something like a combined strategy to improve the simulations in the field.
Thank you, Sidian. We have one question from Chuck Graff online. How applicable would these modeling improvements for the simulation of groundwater or groundwater NAPL situations with clay or shale layers?
Yeah, so I haven't looked at this groundwater NAPL yet, but I think one similar processes here is in the NAPL and groundwater, you also have this flow of two phases, which is water and NAPL. And also you have this mass transfer between the NAPL and groundwater, which is similar to the phase change. But to apply it to this groundwater and NAPL situations, we need to come out with, we need to figure out what's the mass transfer between the groundwater and NAPL. Here we use a phase change behavior to do that, and which might be different if we're going to groundwater enable. Yeah, so which means that for the mass transfer part, we need to use a new model, I would say.
Thank you. Let's give Sidian a hand. We do have a few minutes now to put our presenters on the spot. Were there any follow-up questions you'd like to ask any of the presenters? If there's one, all right.
No, it's not, I'm just trying to ask Sudian, what's the time now in Stuttgart?
It's
11:34.
11, almost 11, yeah.
Woo! Let's give a
thank you
round of
for
applause for
staying
Sidian presenting at midnight. He's more coherent than I'm going to be at that time. Are there any other questions, general questions? Comments? Maybe not comments. Okay, so at this point, we're going to adjourn oral session number 2. Let's give a round of applause to everybody. There's a lot of really, really interesting stuff and groundbreaking stuff. I say that as a modeler myself.